the topic should attract a lot of people. So let me just get ready to introduce you here, Art. Need to move my script in front of the screen there. And okay, all right. Well, why don't we go ahead and get started then? Hello, everybody. Good afternoon. I'd like to welcome you to this afternoon's episode of Restoring the Sciences, the webinar that's sponsored by the National Association of Scholars. I'm Scott Turner, and I'm the regular host of Restoring the Sciences. Today's episode is about climate. What's the physical reality behind our supposed climate emergency, or as it used to be called in less hysterical times, global warming? The common narrative, as we all know, is that it's about increasing carbon dioxide levels in the atmosphere. What about that? Well, we know that there are a lot of things that affect the energy balance of the Earth. To put it bluntly, climate. Things like solar activity, water vapor in the atmosphere, the comings and goings of clouds in the sky, and many other things as well we know affects the Earth's energy balance. So how do we sort these things out? And how do they compare to the effects of carbon dioxide? Our guest today is Arthur Vittorito, who is going to help us sort through some of these issues. He's recently published a provocative hypothesis that tectonic activity, the things that pushes continents around and makes volcanoes erupt, and the attendant leakage of heat from the Earth's core into the oceans is a long neglected, but probably very important factor in climate that deserves to be better known. Let me tell you a bit about Art. He's a renowned climatologist and a physical geographer, beg your pardon. He recently retired from his position as professor of geography at the College of Southern Maryland, and since then, he's joined the Heartland Institute as a policy advisor. I'll be posting some relevant links about Art into the chat box, so have a look at those. Art knows of which he speaks. He earned a doctoral degree in geography from the University of Denver, and his research specialty has long been in climatology and physical geography. Before we get started on our conversation, I just want to share a few housekeeping details with you. Art will begin with a short presentation outlining his thoughts and ideas, after which we'll have a conversation between us. We'll open up the floor for questions from you, the audience, after about 45 minutes. One of our aims here is to give you, the audience, the opportunity to engage deeply with our guests. So I would like to encourage you to put your questions into the Q&A box at the bottom of the screen. We can also accommodate questions in the chat box, but we prefer Q&A because it's a little bit more interactive. And please feel free to put your questions there at any time. You don't have to wait for Q&A to start. Okay, without further ado, welcome, Art, to Restoring the Sciences. We're pleased you're here.
So, thank you. It's a pleasure to be here.
Welcome.
Thank you. It's my pleasure to be here today. Was asked a question by a student a number of years ago and said, "Are we seeing more earthquakes on the planet?" I said, "Well, let me take a look at that. I don't think so, but I checked the literature on that, and sure enough, there it was." I checked the available databases and some of the published literature, and yeah, we do know that tectonic activity has increased on the planet. And I said, well, if tectonic activity is increasing, let's take a look at what's going on under the oceans, because that's where most of the geothermal heat comes from. And after I've been researching this now about 15 years, I realized that we have what I'm calling the geothermal paradox. And the geothermal paradox is a look at the impact of geothermal flux on climate through a mechanism of altering the Earth's currents. That is, the ocean currents tend to intensify when we have more geothermal heating at the bottom, and a deep dive into the literature, pun intended, is worthwhile here. So let me. The geothermal paradox, I state, is how the Earth's second largest heat source may be driving the most recent warming. And until recently, there's been very little research on the impact geothermal heat may have on global temperatures. The vast majority of geothermal heat is emitted by volcanoes and hydrothermal vents in the middle of the world's ocean basins. Now, you'll notice that they occur on these long linear features called the
Art,
mid-ocean ridges.
Art, did you mean to share a screen? Your, are you talking about are you talking about your PowerPoint presentation right now?
Yes,
Okay, because we don't see it.
sorry.
Yeah. There we go.
There we go. We're good?
Yeah, we're good. Yes.
There we go. So as we can see, the vast majority of these hydrothermal vents lie in the middle of the world's oceans. And we see, for example, most of the heat that is supplied by the crust occurs here on the East Pacific Rise, which is off the coast of South America. We see another area here, known as the Mid-Atlantic Ridge, and we see the Southwest Indian Ridge, the Central Indian Ridge, and the Antarctic Indian Ridge down here. So we have these distinct zones, these linear zones, where geothermal heat is released into the overlying ocean. Now, we notice the units here are in what are called milliwatts. So the max areas are about 450 milliwatts, which is about a half a watt, approximately 1/2 a watt. And people say, well, that's really not enough to make a difference. That's not going to heat the atmosphere. But we'll take a deep dive into this one.
So, sorry, Art. Let me interrupt you. We're seeing a Zoom tab. We're actually not seeing your PowerPoint right now. I think you need to share the appropriate screen with us.
Okay.
There we are. There we are. Yes, perfect.
All right. So here we see the mid-ocean ridge system. I have to say the East Pacific Rise, the Chilean Ridge, the Mid-Atlantic Ridge. Looks like seams on a baseball. And this is where the vast majority of the Earth's geothermal heat, as we said, flows into the Earth's ocean bottoms. Here we see a cross-section of one of these, what we call diverging plate boundaries. This is where one plate is moving in one direction, a second plate and a budding plate is moving in a different direction. And here we see magma rising up into what is called a rift zone here. This is all underwater now. And these magma chambers are, of course, connected to what's called the asthenosphere. That is, these are rocks of very, very high heat. And we have slow-moving currents in the mantle that are pushing these plates apart. As they are pushed apart, magma rises up to fill the rift zone in between. Here we can see a close-up of it. We see that these areas contain a number of underwater volcanoes. Ian Plimer estimates there may be as many as 30,000 volcanoes in these rift zones and 30,000 vent fields associated with them. So 30,000 volcanoes, 30,000 vent fields associated with them. Now, we know that hydrothermal systems are known to respond to seismic and magmatic activity along mid-ocean ridges. This is from a study by Davis et al. And it shows that the more seismic activity we have in these zones, the more hydrothermal activity we have. That is, the more seismic activity, the greater the amount of heat that's being discharged into the ocean. Right? This is a really important point because we have very few direct measurements of how much geothermal heat is flowing into the bottom of the oceans. However, the proxy indicator for this is the amount of seismic activity. And the relationship is very, very strong. The correlation is something like 0.97. That is, the greater the number of seismic events, the more geothermal heat that is flowing through the system. Now, the oceans circulate throughout a huge conveyor belt known as the thermohaline circulation. And we know that this is a major transporter of heat to the Earth atmosphere system. That is, we have, in a three-dimensional view, we have warm surface currents, which then subside, move down to the bottom waters, and we see that this all moves around in a gigantic conveyor belt, and this is known as the meridional overturning circulation. This giant conveyor belt is mainly responsible for moving heat and mass around the planet. And if we look at a study by Ballarata, it says that although the ocean is largely heated and thermally driven, at the surface, several recent studies suggest that the ocean geothermal heating can also affect the ocean dynamic and heat budget. By applying spatially constant or variable heat flux of the ocean general circulation models, forced with the present day climate, we can show that oceanic geothermal heat is a significant forcing that can weaken the stability of the water column, warm the bottom water, and strengthen this thermohaline circulation. So if we have more heating down here at the bottom, this conveyor belt will intensify. It will move faster, and this has some interesting consequences that nobody has really looked at. A study by Adcroft and Scott shows that geothermal heating induces a substantial change in the deep circulation, which is larger than previously assumed. The numerical ocean model responds more strongly to in the Indo-Pacific with an increase in meridional overturning of 1.8 Sverdrups, which is 1 million cubic meters of water per second. That is, the overturning of the ocean waters is amplified or enhanced by approximately 25%. So the geothermal heating at the bottom, we know is variable because the number of earthquakes at the bottom does vary. And the more earthquake activity we have down there, the more geothermal heat that is flowing up through the surface. And this is going to tend to amplify the rate at which this thermohaline circulation moves. Now, one thing that we can look at here are the number of seismic events that have occurred in what I call the mid-ocean spreading zones. So I refer to this as MOSA, that is the mid-ocean spreading zone seismic activity. And we track back to 1977. This is when we first start getting reliable global seismic data. And this data goes from 1977, I have it updated up to 2022, and it's culled from what is known as the GCMT catalog. That is the Global Centroid Moment Tensor Catalog. And this is a complete catalog of seismic events 5.3 or greater, and is considered to be a definitive database on the number of mid-ocean earthquakes that we've had. When we plot it back here, we see some very interesting trends. Of course, the overall trend is upward. And we notice that from 1985 down to about 1994, we had a slight decline in mid-ocean spreading zone activity. But in 1995, we have an inflection point. That is, we see that the mid-ocean seismic activity starts to increase, and it has been increasing ever since then. Now here we have plotted was the global temperatures as derived from the University of Alabama at Huntsville satellite microwave sensing database. And we see a large inflection point here starting in the late 90s, 1998, 97, 98 in particular. And if we plot the two curves together, we come up with this. We apply a 2-year lag. That is, the 1977 mid-ocean seismic activity is paired with the 1979 global temperature. the 1980 seismic activity is paired with the 1982 temperature. That 2-year lag is applied throughout the time series, and we see this remarkable correspondence between the two. If we sit down and do a least squares method of linear regression, we see that the correlation is 0.74, which is very, very high. This is statistically significant. And we notice that the mid-ocean seismic activity very closely follows a number of the smaller crenulations or ups and downs in this curve. That is, we see that it pretty much matches pretty well with the El Nino and La Nina episodes that drive these up and down episodes in the global temperature. But again, the overall correlation is 0.74, which is very, very high. And something this high for a system this noisy is pretty remarkable. Now, we sit here and say, what's been the global temperature trend since this one goes back to 1978? And we notice that the global temperature trend has been extremely uneven, geographically speaking. That is, again, this is from the University of Alabama, Huntsville, the microwave data set. We see that most of the quote unquote global warming is really a North Pole phenomenon. The extratropics in the Northern Hemisphere are the second most impacted. They're the ones that have warmed the most. The tropics, lesser still. Southern Hemisphere, extratropics, lesser still. And finally, the South Pole has been virtually no change. So by region, we have seen a distinct north to south temperature gradient in terms of delta T, that is the change of temperature, from 1978 to 2022. Most people don't know this. They think that the globe is warmed uniformly or roughly uniformly, but we see that there are distinct latitudinal bands in this. And my hypothesis shows that we have certain amplifications that we have to look at in this. So if we go back to our thermohaline circulation map, we see that we have two distinct, what I call choke points in the system. One is here in Australia and Indonesia, and we have a choke point here in the Arctic. That is, these are areas where water can pile up and water can then accumulate. In the Pacific region, we see that water can accumulate into what is called the Western Pacific Warm Pool. And up here, it can accumulate in a process known as Atlantification, where warm waters from the Atlantic can accumulate up in the Arctic. We'll get into this in more detail. Next 12 slides will provide concrete evidence that starting in 1995, when we had that inflection in the amount of geothermal activity, as reflected in the seismic activity, we have a host of other geophysical phenomena that have been impacted other than global temperatures. That is, when you see a correspondence of temperature with a bunch of other geophysical systems, something's got to be going on. So first we look at what's called the AMO index, which is the Atlantic multi-decadal oscillator. It looks at temperatures in the North Atlantic, and we see that starting here in 1995, what we call the AMO index suddenly turned positive. That is, starting in 1995, the same year that the seismic activity globally underwater started to increase, we see a distinct jump in the North Atlantic temperatures. And this AMO index cites this very, very nicely. So we are currently in what we call the warm phase of the AMO index, and it continues to this day. This data only is up to 2018. If we look at that AMO index, we see that we have a distinct pattern of warmer temperatures in the North Atlantic, here off the south coast of Greenland, up here into the Arctic Basin, and also out here in the Pacific Basin. So something's got to be going on. We notice the southern hemisphere is very unremarkable, and in fact, we see that there's actually been a little bit of cooling down there, at least in the southern hemisphere oceans. So this brings us to a study by Ozil et al. That says the Arctic marine biome, shrinking with increasing temperatures and receding sea ice cover, is tightly connected to lower latitudes through the North Atlantic. By flowing northward through the European Arctic corridor, the North Atlantic waters transport most of the ocean heat, but also nutrients and planktonic organisms towards the Arctic Ocean. Using satellite-derived altimetry observations, we reveal an increase up to twofold in North Atlantic current surface velocities over the past 24 years. This was published in 2020. The first submission date was 2019. That is exactly 1995. This is where they start to notice an increase in current surface velocities, i.e. they're noticing here that the thermohaline circulation appears to have intensified starting at exactly the same time that global seismic activity also intensified. We see here that the AMO, the multi-decadal oscillator, had an abrupt change in 1995, and it's reflected in hurricane activity. We are now in the warm phase here. You can see it starts here exactly in 1995, and we see what we call the North Atlantic ACE, accumulated cyclonic energy, jumped up in 1995. That is, once the North Atlantic started to heat up, more hurricane activity, more energetic hurricane activity was occurring in the North Atlantic. We see here that the cloud cover in Greenland also started to decline abruptly in 1995. That is, as the overlying atmosphere started to heat, the humidities go up, but the cloud cover actually goes down because it can hold more heat. It can hold more water vapor with higher temperatures. We see that global cloud cover actually started to decline starting in 1995. Again, this is a function of the fact that with a warmer global temperature, it can hold more water vapor, which then serves as a feedback to warm even further. We see here that the breakup and freeze up dates of ice in the Hudson Bay region also abruptly changed in 1995. The lines, I think, are very clear on this one. We can see here that we saw a rapid warming of what's called the subpolar gyre commencing in 1995. This is the large gyre of water sitting off the south coast of Greenland. This is what this looks like. Here's the SPG here. You can see that. And we can see here starting again in 1995, an abrupt increase in the temperature anomaly. We also see here that of latitudes 80 degrees and higher, we see that in 1995, we see a distinct jump up in the spring and the fall temperatures. Here's our breakpoint here in 1995. And the winter temperatures follow a little bit afterwards. They start jumping up at around 1999, 2000. So the winter temperatures were a laggard in this, but nonetheless, the fall and the spring temperatures jumped up abruptly again in 1995. So we're seeing a sort of coalescence of effects starting in 1995 that are all related to an enhanced thermohaline flow and a concentration of heat in the Arctic region. Here we see Northern Hemisphere sea ice also started to decline. This is from the National Snow and Ice Data Center. 1995, again, is our inflection point. That is, things were flat up in here until 95. 95 takes a dip down, and from 95 on, it's been moving towards lesser snow and ice cover. Now, out in the Pacific, the enhanced thermohaline flow also causes more warm water to accumulate in the Western Pacific. That is, the physiographic and bathymetric features of that region block, shall we say, or restrict the flow of the equatorial current, creating a reservoir of warm water, and that warm water is a driving force behind El Nino events. So here we see the equatorial current coming off of the west coast of South America and North America. And here we see that it terminates here off the east coast of Asia and Australia. This gives rise to what we call the Western Pacific Warm Pool. Sitting off the coast of Indonesia and Australia, warm water is allowed to pool off the coasts. And that warm water pool provides the fuel for El Ninos and another interesting event, that is the warming of what we call the Kuroshio current, which is a very, I'm realizing now, is a very, very important dynamic. Here we can see a study that showed the heat content of the Western Pacific warm pool in 1993. This is this top. We can see that it's relatively cool, and the warm pool is relatively small. Here in 2014, we see that the warm pool is much warmer, and it is much larger. So that is, again, in between 1993 and 2014, we see that this Western Pacific warm pool has expanded and has gotten warmer. We also see, abruptly after 1995, a change in what's called the thermocline depth in the Western Pacific. The thermocline, of course, marks it's the dividing line between warm surface waters and cooler waters sitting underneath that. And we see this abrupt shift of about 10 meters or 30 feet in the thermocline depth. That is, after 1995, the thermocline depth got deeper, and you would expect that with an enhanced Western Pacific warm pool. So basically what's happening is the Western Pacific warm pool has gotten bigger and is storing more heat. That warm pool is then, under certain atmospheric conditions, is able to expand, and that expansion gives us the El Niños that we are currently experiencing right now. The El Nino effect, as we know, is it's called a sashing effect. That is, warm waters from the Western Pacific warm pool will sash back or flow back into the Eastern Pacific, causing anomalously high temperatures in the Eastern Pacific. Also into the Northern Pacific, it extends up the coast into the North America region and down here into the South American region. The Kuroshio current is also strengthened when we enhance the Western Pacific warm pool. When there is more heat in that Western Pacific warm pool, we see an intensification of what is called the Kuroshio and the Kuroshio extension. I'll show you what that looks like. This is the Kuroshio current. It starts here just north of the Philippines. That is what we call the Western Boundary Current. It washes the water off of China, Japan, and its extension comes all the way across the Pacific to the coast of North America. And this is a study that was done by Adrian Lamb, and it shows that warmth stems from the surface waters that collect in the Western Pacific Ocean along the equator, called the Western Pacific Warm Pool. The Kuroshio current takes these waters north past the Japanese coast and then eastward at the 36th north latitude, where it joins the open Pacific Ocean. At this point, it becomes what we call the Kuroshio extension current. Today, these currents are warming 2 to 3 times faster than other areas of the ocean. Ocean model studies and observational data also show that the Kuroshio current is shifting northward and increasing its transport capacity. Again, this is all in line with an enhanced thermohaline flow. More geothermal heat is enhancing that Western Pacific warm pool, which is causing the Kuroshio current to strengthen and to intensify. It's transporting more heat and it's transporting more water too, more wet, more mass. And here we can see this. This is from April. Here we see this Kuroshio current and the Kuroshio extension extending almost across the entire North Pacific. So the following slide is going to highlight all the main hotspots that we'd expect from enhanced thermohaline flow. And this is a snapshot from last month, August 18th. And first we'll look here at the black boxes. The black boxes up here point to this Atlantification process, which causes what we call the Arctic amplification. We can see the warmer temperatures up here in the Arctic basin. The white circular area is that subpolar gyre that we had talked about. We can see here, this is an area of higher temperature. It also spills over into the Hudson Bay region. The green box is the Kuroshio current. We can see that the Kuroshio and its extension is a band of warm water stretching across the North Pacific. And then finally, we have the anomalously warm temperatures that we're currently experiencing with the El Nino, and it's a what's called an El Nino 1-2 event. It's in this easternmost zone of the Pacific Basin. So we can see these sort of current hotspots, all related to these enhanced currents around the globe. It makes perfect sense, and it fits in perfectly with the idea that we have an enhanced thermohaline flow, which is backing up, which is impounding more water on the Western Pacific warm pool, which, by the way, has started to dissipate already, and is also causing more water to become impounded into the North Atlantic and into the Arctic. So in summary, here is a hypothesis that is currently sort of my life's work as a retiree. Greater mid-ocean geothermal heat is caused by and is also a result of greater mid-ocean seismic activity. This greater mid-ocean seismic activity, which we've well documented, intensifies the thermohaline circulation. In the Pacific, which we see here on the left-hand side of the flow chart, the intensified thermohaline circulation causes increased oceanic heat transport into the Western Pacific. This amplifies our El Ninos, and it causes the Kuroshio current and its extension to warm, and this results in increased Pacific tropical and extratropical temperatures. On the right-hand side, this is the Atlantic side, we see that increased oceanic heat transport into the North Atlantic and the Arctic as a result. This process, again, is called Atlantification. We have less snow and ice cover, which lowers Arctic albedo, and we increase the North Atlantic and Arctic temperatures. So we see two distinct pathways for this. And the data fits, what we're observing fits very, very well within this framework. Now, critics have jumped on this for a couple of reasons. So I want to quickly share what some of the main objections to this are. First, I said there's not enough heat escaping to the surface to directly warm the overlying atmosphere to an appreciable degree, okay? And secondly, they say the high correlation between mid-ocean seismic activity and global temperatures doesn't signify causality, as spurious results can arise if confounding variables are omitted from the experimental design. Okay, this is peer review talk. These criticisms are easily refuted by the following arguments. Although there isn't enough heat to directly warm the atmosphere, we have modeling studies that show that oceanic geothermal heat intensifies the thermohaline circulation. That intensified heat flow acts as a heat pump to distribute an increased amount of oceanic heat to two major heat sinks, the North Atlantic / Arctic, which is called the Arctic amplification, and the Western Pacific warm pool. We have irrefutable empirical evidence to corroborate the modeling results. And to address the second point, the entire chain of environmental changes, i.e. higher global temperatures, reduced ice cover, amplified El Ninos, etc., is anteceded by the change in mid-ocean seismic activity by exactly 2 years. This is what we refer to in statistics as Granger causality. And it strongly infers that a cause, i.e. one change, in this case, the change in mid-ocean seismic activity, drives time-dependent effects, in this case, other perturbations that occur afterwards. And I think we have completed that cycle of events. We have connected them, I think, in a very reasonable way. In other words, the physical evidence backs up the statistical evidence that we presented. So we've got an epistemological problem here that is understanding the climate really is a classic geophysical problem, and it's in all of its glory and all of its complexity. That is, we're just now beginning to understand the role of plate tectonics, solar variability, subaerial volcanic activity, submarine volcanic activity, changes in the thermohaline flow, and of course we have Milankovitch cycles. All of these factors have to be considered when we consider climate change. And to quote Alfred Wegener, scientists, and this is from 1929 in his Origin of Continents, scientists still do not appear to understand sufficiently that all Earth sciences must contribute evidence towards unveiling the state of our planet. It is only by combing the information furnished by all the Earth sciences that we can hope to determine truth here. I mean, it was true back in 1929, and it clearly is true today. If we're just looking at carbon dioxide as a control knob, and I know Judy Curry talks about this all the time, she laughs at it, is very naive, and I think it's a total corruption of the scientific method. Thank you.
Thanks, Art. That was fascinating. We've had one comment in the chat box that says this is from Dave Peterson. He says this is fascinating. Seems much better science, more parsimonious than what I've read on the greenhouse gas theory. And this ties into what you were just saying about the arguments from your critics. Now, I used to teach a module on climate change in a course I taught when I was an active faculty member. The course was Physics of Life, and we spent some time talking about climate and how it works. And certainly, if you look at the paleoclimatological data, it's very clear that changes of ocean circulation are the drivers of global climate. And so in order to make the connection between increased atmospheric CO2 and climate change, you have to somehow tie in the effects of atmospheric CO2 to being able to influence these major patterns of circulation in the oceans. So I've never found that connection very solid. What can you tell us about that? I mean, is this a weaker link than everyone is saying?
Well, interestingly, if you just look at the patterns of warming, that last slide that shows the sort of the hot spots on the globe, those hot spots are all very aligned very well with ocean current configurations. In other words, the heating is geographically, I think, well prescribed. If carbon dioxide was driving this whole thing, I think you'd see a much more even distribution of temperatures around the globe, and you see a much more even distribution of temperature change. But here we see very concentrated warming in the Arctic and in the North Pacific, and it's all tied with changes in sea surface temperatures and current intensities. And these are current driven, and those currents, we know, although largely driven by wind circulation at the surface, about 20% is driven by the thermohaline process. In other words, what's going on underneath the whole system. It's a conveyor belt, it's all connected, and it's been largely ignored, and it's been widely criticized since I put up with this. Some of the arguments I've got for this are kind of ridiculous. It's like, well, it's you get mostly diffusive heating at the bottom. You don't find convective. No, they estimate up to 30% of the bottom waters do convect when you have hydrothermal episodes. So there's a lot that is just a sort of passed over lightly or glossed over without any real understanding of what's going on. And to me, this is the last great frontier for science, especially climate science.
Art, could I ask you to stop sharing your screen so that we're more than postage stamps up on the corner of the screen?
Gotcha.
Yeah. There we are. In all our glory. Great, thanks. So it might be useful to maybe elaborate on this term that you use, thermohaline circulation. And of course, the thermal circulation is quite straightforward, but the haline part of it might not be so evident to our audience here. So what can you tell us about that?
The thermohaline, of course, is a conjoined word of thermal, which is heat, and haline, which has to do with soil content. So, for example, if you start to push more water from, say, the southern hemisphere into the northern hemisphere, which is pretty much the direction of the prevailing currents, in the southern hemisphere, they're going to heat up, south of the equator. When that happens, you're going to start to evaporate water, and that's going to increase the salinity. So you've got an increase in temperature and an increase in salinity, but then as you get further and further north, it's going to hold that temperature, but at the same time, as you hold that temperature, you're going to evaporate more water, which is then going to increase the salinity. By the time it gets up into the polar regions, now it becomes so salty, it becomes very, very dense, and it starts to sink. And that sinking of the Arctic waters is what drives this. That is considered to be the sort of the main cog in the wheel of all this, the sinking of water. In fact, they talk about this. Michael Mann talks about this a lot. He says, well, if we continue to heat the planet up, it's going to shut down the thermohaline circulation. In particular, they talk about what's called AMOC, the Atlantic Meridional Overturning Circulation, that part of the circulation in the North Atlantic. And if that shuts down, then you've got a lot of water just accumulating up in the Arctic. It doesn't sink, and the current systems all slow down. And they claim that that's going to cause more ice to form, which is probably correct. And it's going to plunge us into an age of global cooling. Yes, no, there are arguments on both sides of that too, on both sides. But nonetheless, they know it's a main driver. Everybody knows it's a driver, but yet they ignore it.
Yeah. The thing about this thermohaline, well, this Mann hypothesis that we're going to somehow shut down the global heat conveyors, is that it's inherently self-limiting. You know, as you said, if you shut down this conveyor, then you're going to have colder temperatures in the Arctic or the polar regions and hotter temperatures in the tropics and semi-tropics, which of course will just limit, well, actually kind of choke off this problem, because then you'll get accumulating snow and ice and glaciation and so forth. And so you would expect, if that was true, you would see kind of a very clear oscillation of global temperatures. Now, I've seen patterns of estimated global temperature from paleoclimatic data, and there does seem to be this kind of switch that's being activated, which of course is consistent with this with the Mann hypothesis. But is that really what's driving climate now? I mean, those timescales that I see in the paleoclimate data are very, very long. You know, these are the kind of things that govern ice ages and interglacials. So is that hypothesis, does it provide you the necessary time frame for it to be plausible for our present situation?
Interestingly, most of those, as you said, those very long time frames, we know that orbital variations are the main drivers. They're the Milankovitch mechanisms kick in. So, for example, we have noticed over the last about 4,000 years that global temperatures have been trending downward, with, of course, spikes up, spikes down, spikes up, spikes down. But that the overall trend is down. That is where it looks like we're heading to the next ice age. And they've tied that in with the obliquity, that is the changes in the axial tilt. That is the axis, as it becomes less tilted, as the axial tilt declines, what that tends to do is it tends to lessen seasonal contrasts. And when you have lesser seasonal contrast, that leads to cooler temperatures globally. And the way that this works is very simple. If you have, in the Arctic, if you have cooler summers and warmer winters, the temperature contrasts are minimized at that point. And what will happen is you'll get more snow in the winter, and you will get less melting in the summer. And net, you will accumulate snow and ice on the planet, and that starts to push you towards a snowball Earth situation, where that is an impending glacial age. So those lessened equator to pole temperature gradients do engender, they do set in motion the factors that you need for the next cooling period.
Yeah. I'm going to share something on my screen as well, just because I happen to have been looking into patterns of Arctic sea ice, and this is for something about polar bears and whether they're endangered or not. So I'd just like to share with you something from WhatsApp. I think I need to minimize a couple of other windows here, but let me just try that here. Here we are. Okay, here we are. Yes, okay. I think people should be able to see this now. Is that graph evident?
Yes.
Okay, so this is extent of sea ice. This is from a Norwegian climate group, and it's based upon satellite data. And this middle curve right here is the extent of Arctic sea ice, and you can see that it starts at 1979, which is about the same time frame that your data are coming from, primarily because we have new instruments coming online all the time. And certainly Antarctic sea ice has been declining over a period of several decades. And of course, that's what's getting people all concerned about polar bears. But then in the last 3 years, you're starting to see it increase again. Is this in the time frame of the kinds of things we could expect from, say, variation of tectonic activity? Do you think that could be explained by that? Do you think that's a signature of tectonic activity?
I think what I've read on this is that as you reduce the amount of sea ice, the polar bears actually do quite well. Susan Crockford, I think, has promoted this, that as you reduce the amount of sea ice, there's still enough sea ice out there for the polar bears to work with, but there's more land area, and they will hop from one ice flow to the next, and it doesn't matter. If you completely de-ice the Arctic, then they've got a problem.
Yeah.
I mean, one of the places we're having the biggest polar bear problems are in some of the populated areas around Hudson Bay, because they love the trash. And so you do have that interesting sort of paradox there. So I do think that I think the polar's been around for a long, long time. I think they're pretty well adapted to what's going on.
Yeah, and this is also tied in with one of the concerns that I have. I mean, I'm a biologist, you're a physical geographer, and part of my concern about the whole global climate scenario that's driving things is that and I'm not putting down physicists here, but that it actually is dominated by physicists who might not have as much of an appreciation of the effect that life has on the climate. I mean, if you look at our atmosphere, something as basic as that's a construction of life on Earth. And coming back to polar bears, we seem to forget just how adaptable living things are at creating their own environments and actually mitigating these effects. So life seems to be the big missing variable in a lot of climate scenarios. You have a lot of biologists kind of proposing that, oh, this is going to do this or that, insects are going to disappear, or all kinds of things like this. But that really, I think, underestimates the adaptability and resiliency of life in these systems. And polar bears are certainly a prime example of that. If you look at the different polar bear populations, there's a variety of conditions of sea ice and fjords versus on Hudson Bay, and in some of these other areas that you're talking about, different sea ice conditions, and yet they seem to do just fine. They seem to be able to figure out how to actually hunt in these different kinds of conditions. So that's just my little hobby horse there, that we really need to realistically bring life into our climate science as well. And certainly the physics is important, but we don't really even know the physics of it, as Alfred Wegener said. Isn't that right? Yeah. Okay, so let's go to some of the Q&A then. I already mentioned Dave Peterson's comment that and I certainly would agree with him, that this is fascinating, that if we're going to have any understanding of climate at all, we have to kind of broaden our minds beyond greenhouse gases. There's so many things that are driving climate that we without considering all these other things, we really don't know what we're talking about. And this leads into the comment that Consolato Sergi has posted. He's saying that it's the process of understanding science that has been politicized. He goes on to say that Bacon, Descartes, and Galileo were teaching about the scientific process. I agree that, and these processes are rarely taught at the beginning of the science courses. So just thank you, Art. Really fascinating. So I think what that's leading into, two questions really, is are we teaching students properly about the incredible complexity of these systems, and have we really corrupted climate science with politics?
I think there's been a very heavy corruption of the scientific method, and also there's been it's been heavily politicized. I found a lot of my students. One of the reasons I retired, I think I still have a little gas left in the tank, but one of the reasons I retired is because it was very, very hard to break through to a lot of these kids on any rational, objective level. They come in here they would come to the classroom filled with all sorts of crazy ideas about CO2 is causing it to warm. There's no doubt about it. The ocean's going to boil, and there was no breaking through that. I mean, this is what they were indoctrinated to know. So yes, it's become politicized. It's all about money and power. If you control the climate, the way that you control it, of course, is through the energy production and energy distribution system. When you control that, you then control the agricultural systems, the transportation systems, et cetera, et cetera. And this becomes a very, very powerful political, military, economic tool that people, of course, are jumping on, and they definitely want to work with. And I'm sort of appalled by it, and I'm frustrated by it, because you can't seem to break through to a lot of folks. They don't want to hear about it. And it's very hard to get to know where to turn. As they say, it's a lot easier to tell somebody a lie and get them to believe it than to get them to understand the truth after they've accepted the lie. I mean, that's been said before. So we just have to keep putting out, I think, good science, and hopefully in the end, good science will win, and good science will start to convince people that what they're saying is going to happen isn't really going to happen. Every day when I look at my data, I say, geez, I wish these earthquakes just turned down and the global temperature turned down with it. This way, it puts a lot of things to rest. Of course, as an objective person, like, no, we have to sit there and report it as we see it, and just come up with better ways to explain it, or come up with a better understanding of this. And also, too, what we've done is, I think we've also corrupted the peer review process. I think the peer review process has become a highly corrupt system. I call it steer review. It's not peer review. Where they get these editorial boards up there, and they steer things towards a certain agenda, or to a certain canon, so to speak. And if you're not in that direction, if you're not working in that area, it's done. It's over with. I've proposed things that can improve that. If you're going to join a professional society, you then have to agree to, in order to keep your standing as a professional society, you have to agree to review so many articles within a certain time frame, and open the peer review process up, make it more like a jury system. But no, right now it's a very tightly controlled system, and it's very autocratic. So I think that has to change too.
Yeah, there's this thing that's been circulating around for the past couple of days. This climate scientist, very fine scientist, basically confessed that, I don't take back anything I wrote in this paper to Nature. I'm just doing a quick look to see if I can find a link to it here. But I definitely had to tailor my message to the editorial wants of the editor. So yeah, I think I'm going to remember steer review, because that's a very good thing. In fact, I'm probably going to steal it from you. But these things haven't happened on their own. I mean, I, like you, have had a long multi-decade scientific research career. And I've noticed the kinds of changes that you are describing. And these aren't just forces of nature. And that raises two questions. What did it, first of all? What was the driver of this? And secondly, how is it that we can actually reverse that and bring back integrity to science, in particular climate science, which is, I think, high on the list of sciences that have been corrupted?
I think it's going to be a tough slog, as they say. I think what's going to have to happen is somebody's going to have to sit down and say, okay, we're going to have a true review process and have a peer review journal that is going to accept all points of view on this. And we're going to work with that. And we're going to try to establish ourselves as the purveyors of real truth in this whole thing.
Mhm.
I'll never forget a story by someone who was received his he was tenured, and they had a little party for his tenuring. And we says, "How did you do it?" He only published a few articles. He says, "What I tried to do is I tried to revive this whole eugenics idea." He said, "Of course, it's totally wrong. It's totally off the wall, but I got a tremendous number of citations because they use the science and social science citation indices to award tenure. And what he did is he took a contrarian position on it, a totally contrarian position, and got a lot of attention. Of course, it was all negative attention. It was all criticism, but it got him tenure." So also, yes, the article you're referring to, I think, came out. Was it Science or Nature? One of the two big
It was
ones.
nature. Yeah.
Yeah, it was Nature,
Mhm.
and that's horrible. That's absolutely horrible. In trying to get my initial paper published on this, nine journals flat out just rejected it. Four of them wouldn't even review it. Five, one one review I got back from a highly esteemed journal said, "Well, this is kind of interesting, but don't you know that carbon dioxide is what's causing the climate to warm? Why are you talking about this?" It's like, well, whoa, whoa, whoa! I've got a whole different idea. Have you even considered this? No, we're not going to consider it because it's way off base, and that was the end of it.
Yeah.
So I had to
Yeah.
publish in an open access journal, and I got a
Yeah.
much fairer review on it.
Yeah. Yeah. What makes me break out in cold sweats at night is of course the inexorable demographics of the situation. People like you and I, let's face it, we're on the right hand side of the demographic curve, and just as the students that we're seeing are seem to not be interested in some of these fascinating scientific details and taking a skeptical look at it, the same kind of thing is happening at the junior ranks of the faculty. And again, I come back to the question: how is it that we can actually restore these kinds of scientific ideals so that we can get back to a rational discussion about climate, eugenics, intelligence, a whole host of other kinds of verboten ideas? How do we do it?
Yeah, it's as I said, it's a tough slog, and it's going to. I mean,
Yeah.
we did go through a dark ages at one point, and we may be on the brink of another dark age here, where
Mm,
what does that song say? When logic and proportion have fallen far from view, and I think
mm,
we're getting there.
yeah. Oh, that's a depressing thought, but still hopeful in the long term. So coming back to some of the questions, then Dale Schaefer asks, is there evidence that it's water flow velocity that's the mechanism of increased global heat transfer? And so we're talking about increased heat input to the water, warming it, and then of course heat transfer. Heat transport is connected to mass flow as well. So is it speeding up the circulation?
Yes, in fact,
Mhm.
a paper came out about 6, 8 months ago in the Proceedings of the National Academy of Sciences that said that all of the global currents have increased in their velocity, all of them.
Okay.
And
Okay.
they come up with a very interesting reason. Well, it could be due to the fact that due to global warming, we're compressing the atmosphere, and it's sort of like it's like a Venturi effect. We're pressing an atmosphere through a smaller. It's like that doesn't make any sense to me.
No. No.
So that article has been published, but it is well documented that the what you have is more heat being transported. The water
Mhm.
is warmer, and it is intensifying. There is
Yeah.
a greater volume of flow.
Yeah.
More
Yeah.
sphere droops are being passed through the system.
Okay, that answers, I think, Dale Schaefer's other question was he'd like to see the flow data, and apparently it's in that paper that you just mentioned, right? So, okay, so we're coming to the end of our time here. We've come to the end of our questions. Speaking of how you deal with um, this problem of restoring the integrity of the sciences. So before I turn over to you, Art, for your final thoughts, I've put some links to some pages about Art on the chat box, so please have a look at them. And then I'm going to put in a plug for the Restoring the Sciences webinar for next week. And this is directly germane to the questions that we're talking about. Those things are up there right now. We're going to have two guests on Restoring the Sciences, Bernard Trout of MIT and Luana Moroja at Williams College, and they were two of 29 co-authors on a paper that came out a couple of months ago in the Journal of Controversial Ideas. And Art, you mentioned you had some difficulty finding a journal that would be willing to open their minds a bit. This was a similar kind of situation with this paper. It's called In Defense of Merit in Science, and there's a link to it on the chat box. And they had a similar experience. You know, the question was in defense of merit in science, and 4 or 5 journals found that so controversial that they couldn't possibly consider even reviewing it. And so it ended up in this interesting journal of controversial ideas. So this issue seems to be endemic, doesn't it? It's one of these things where we've kind of settled into a new way of thinking about things. I'm not sure it's a good way, and let's hope that we can actually turn it around sooner than the amount of time it took for us to get out of the dark ages. Okay, so this video, our conversation will be posted on YouTube shortly after we get done here, and that's a good place to add more comments and questions. So I would encourage you to, you in the audience, to have a look at that. We do monitor it and try to answer any questions or comments that come up. And as I say, that will be up very shortly. Please do share with your friends and colleagues because I think a lot of people need to hear the message that Art has given us. And next week we'll have, as I said, 2 of the co-signatories of this interesting paper as our guests on Restoring the Sciences. And I put up links to register for the webinar there, as well as a link to this paper. And the last thing I'd like to mention is to put in a plug for the organization that sponsors our webinar today, the National Association of Scholars. If you're already a member, thank you very, very much. If you're not yet a member, we would welcome you to join, because we're kind of a fun, interesting group, in my opinion. And so please do that. All right. So Art, again, thanks so much for this fascinating discussion. I'll leave the last word to you.
Thank you, Scott. It's been a real pleasure. And yes, I would also like to put in a plug for NAS. You folks do wonderful work out there. Your publication was Academic Questions. There's first-rate stuff. I enjoy reading that, and I think you're doing a wonderful job. This is the kind of thing that has to happen, and I would support any and all of your efforts. I think you should have as many of these as you possibly can on you know, the total range of this subject. And just keep in mind that as a final thought, Alfred Wegener, who was my sort of one of my intellectual heroes out there, wrote a book on the drifting of continents, and it got him banned from any teaching or research job he ever could. And he died with a smile on his face. And it took about 30 years, but eventually his ideas were embraced. So it's just planting the seed could be enough. And if we plant enough seeds out there through this organization, I think eventually the truth will come through.
Yeah, I think intellectual courage is the key there. And I'm looking forward to those smiles coming back on our faces. So Art, thanks very much for joining us.
Thank you,
and
Scott.
To all of you, thank you for joining us as well. And I hope to see you next week in Restoring the Sciences. Good day to all.
Thank
Bye.
you.
Bye.